Hello and welcome to another episode of Risky Business. Last time we were going to experiment with a few things. So let me see here. Okay, so I know there was some stuff with GPIO here that I was wondering about. There's GPIO input EN, output EN. Okay, and what else? I feel like there was something else that I was wondering about. Oh yeah, this LEDs variable. I think that's just dead code. So I want to investigate that as well. So we should probably start there, I guess. Yeah, so I'm just going to comment this out and see what exactly that does. Okay, so what all do I have open right now? I'll just open another terminal. So let's build this program here. Oh, I need to be up here, don't I? There we go. So I think that looks good. Let me plug in my Hi-Fi 1. All right, and actually I have the LED demo on there, so I should probably make software clean. And then we'll upload that to the board. Okay, so I am getting the blinking lights. So the LED is behaving as we expect. So yeah, I'm pretty sure this line was just dead code. The compiler could optimize it away, and compiling it out doesn't seem to change the behavior. So now, my next question is input en and output en. So, I mean, output enable seems like something that we're definitely going to need. But input enable, I don't know why that's there. So I want to turn that off and see if it makes any difference. Alright, so again, didn't seem to make a difference. I feel like that line is probably not necessary. Maybe it was a holdover as well. But now I do want to see what happens if we also comment out output enable. Yeah, so when that's commented out, the LED does not light up at all. So we do need to enable output on those bits in that register to be able to get color out of our LED. So that makes sense, I think. I want to look at this documentation again. So output en is described as pin output enable. So it seems that simply to be able to send output over those pins, it needs to be enabled in this register. Otherwise, it just won't do it. That's my understanding of that. So from there, there's a few things I want to look at. We understand that, like, we understand everything these lines are doing. And we understand where was it? This stuff right here. So we understand this as well. But we saw in the LED fade demo that if you want to mess with the intensity of the color, you need to go through like PWM stuff that we haven't studied yet. So we might want to look at that. And the other thing is the output that I'm printing to the terminal here. This is, again, because we're on the demo GPIO program, it goes through the UART init, and it runs at this fast speed, right? And as a result, it isn't able to read from the OTP. And we know that using the OTP divider, we could potentially get it to properly read without changing the speed of the core. So we might want to mess with that as well. But I think since we're doing LED stuff right now, maybe it would be better to jump into studying the PWM stuff. And then there's also this bit banging. So, I mean, we can take a brief look at this. Like, we understand what this line is doing. It's the exact same thing that we're doing, like, right here, right? Or, I guess more accurately, this one, because it's the output enable register. So for pin 19, we're just enabling that in the output enable register. So we can bit bang over pin 19. And let's see, we do the PLIC init, we reset demo. So that all makes sense. Then we have a mask, and again, it's just the pin 19 bit. And so what are we doing? We're doing an atomic fetch exclusive or explicit, which we don't know what that is yet. And so this macro dereferences, so we have the GPIO output val register, memory mapped register. It's adding to the GPIO base address and then dereferencing that. But then we're taking the address of that. So we're undoing the dereference that the macro does here. And just getting the address to that the memory location of that memory mapped register. And so this function here, atomic fetch exclusive or explicit, it takes a register, an address to a memory mapped register. it takes a mask, and it takes a memory order. So we don't really know what that's doing without diving into the atomic fetch exclusive or explicit function. So I think we will come back to that when we study atomics. As far as the GPIO related stuff, we understand everything going on in this program regarding GPIO now. So yeah, I mean, we understand everything in this program. The only thing we haven't studied in depth is some of the stuff that goes on behind the scenes and this one line right here. So the next thing I want to do is look at LED related stuff in the LED fade demo. So let's close out of that program and go to the LED fade demo. I guess I already have that open. Yes, I do. Let's close this terminal. We don't need that one. All right, so let's start studying this new program here. So a lot of this stuff is going to tie in to the other program when we get under the hood a little bit further of the demo GPIO program, seeing how it's all the initialization stuff that happens. This program is doing it a little bit more explicitly. They have a putC and getC function that they declare that's doing UART related stuff. And then they have a putS function that uses putC. So instead of using write that's provided by the SDK, they're explicitly implementing a string printing routine. And then you can see they do all the setup stuff for like the UART and GPIO and setting up the speed and everything. But the part I care about is the stuff relating to LED. So again, we have these 16-bit variables on the stack here, R, G, and B. I don't know why they're 16-bit. I'm sure we'll figure that out soon. So we set up RGB PWM right here. So we're going to study that. There's some more stuff happening here. Okay, so here's some new stuff relating to LED with GPIO. So we're using the output exclusive R, which I don't really understand what that's for. Like, I understand what an exclusive R is, and that it's apparently like messing with the output, but I don't see the purpose of that register right now. And then there is GPIO IOF cell, so select I assume, and then enable. So let's look at the documentation here. So there's IOF enable and IOF select. It's setting the output to be inverted. Hossein, I can understand that. Like that's what we do in the other demo. we invert the LED, but we don't use a special register for that. We don't use output exclusive R. We just invert it directly. So I don't understand why there's an output exclusive R register. Why you would invert the output using a separate register rather than just using the output register directly. That's what I don't understand. So IOF select and enable. These are hardware IO function, enable and select. So let's look at this documentation here for IOF. Each GPIO pin can implement up to 2 hardware-driven functions. So what this is saying is that the GPIO pins can implement some special hardware functions, and you can have them do them using these control registers. When a pin is set to perform an IOF, it is possible that the software registers port, output enable, pull up, DS, input enable may not be used to control the pin directly. Rather, the pins may be controlled by hardware driving the IOF. So which functionalities are controlled by the IOF and which are controlled by the software registers are fixed in the hardware on a per IOF basis. Those that are not controlled by the hardware continue to be controlled by the software registers. If there is no IOFX for a pin configured with IOFX, the pin reverts to full software control. So, okay, that makes sense. And where is it documented? Like, I'd imagine the Getting Started guide has documentation about which ones have IOF related stuff. And it looks like kind of, it says there's this IOF 0 and then IOF 1. Okay, so these are the 2 different IOF that each pin can be programmed to have. So if we look at the green, blue, and red pins, we see that there's these PWM on IOF 1, PWM 1.1, 1.2, and 1.3. So those are the IOF functionalities that we're messing with. Okay, let me read your comment now, Hossein. Because in the schematic of GPIO, the exclusive OR is in the pin data path. In other words, you have the option to invert the pin value by hardware. You can obviously for the same thing in software. Okay, so you're saying that it's the hardware way to do it. So they have that functionality baked right into the hardware. So what we're doing in the demo GPIO, we're doing it by software, of course. But the point is that you can also directly invert it through hardware. So when you say the schematic of GPIO, is this something like I don't know if GPIO is standardized outside of like what we're doing here. I know this is all compatible with Arduino, but I don't know the hardware background of this. When you're talking about the schematic of GPIO, are you talking about the schematic in the risc-v documentation? I don't remember where that was, but like this one right here? Or are we talking about like a more general specification of GPIO? Because, like, is there a technical reason? Okay, so this figure right here. Is there a technical reason that we need the exclusive OR in the pin data path? Like, I still don't understand why this would be implemented in hardware. Like, I guess maybe performance, if it's faster than doing it in software. But other than that, I don't know why that hardware would be in there. So you're saying it's pretty standard in ARM and other MCUs. So it's just because it's standard then? Like, I'm just trying to wrap my mind around why that's in the hardware, I guess. Like, to me, it seems like a thing that you could just not have that hardware and only do it in software. And, like, I don't know if there would be a significant reason why you'd want it in hardware. The only thing I can think of is if it's like a performance issue. Or if like the circuitry needs to be there for something else, and so it's trivial to allow this functionality. Like you get it for free. I don't know. um, but yeah, anyway, the other thing we're looking at here is these IO functions. The getting started guide lists out what it has, but it doesn't necessarily say what they do. Unless that's somewhere else. So I'm not seeing something in here that talks about what the PWM, like what the IOFs do. Okay, so you say you think it's because of performance, because bit operations in C needs a couple of instructions to do the same thing. Okay, yeah. So that would make sense to me too, that it would be a performance thing. I imagine that with GPIO related stuff, like you want to be able to push as much as you can over the pin as fast as you can. That's what bit banging is all about, right? And that's like the example that we saw that I think his name was Bruce, the guy that did a YouTube video of having the Hi-Five 1 drive some speakers. Like, I imagine that's really pushing a lot over those pins, And so if it needed to do an exclusive OR while it's pushing those over the pin, performance would be very important for that kind of thing. And so that does make sense why, if that's a bottleneck, it would make sense to have it in hardware. So I think at this point we need to study PWM to really understand it more. So for IOF select, we're setting on the bits for each one, and I believe that toggles you to IOF 1, and then IOF enable for those three. So that's saying that we are not really controlling these pins in software like we were doing in demo GPIO. We're using the IOF hardware to control the pins. And the hardware that we're using is these PWM things. And so to understand those, we probably need to understand the PWM, I would imagine. So it looks like that's everything we're doing with GPIO in here. So let's dive into the PWM tonight. So I'll start at Carplex and work our way down. So let's see if this is anything about PWM. So IOFs are to set the functionality of the pin. Because you just have a few physical pins on your chip, you can't have a pin to do only GPIO or UART or SPI or PWM. So the IOF selects what functionality you want from that pin. So basically it's just a muxer, right? It just multiplexes where you say, I want to do a specific thing on this pin. Alright, so I don't think there's anything about PWM in the Carplex, so we need to go more specific. So here's the E300 platform. Okay, so this has a power management unit. That's PMU, not PWM though. I am looking for PWM. Here it is, pulse width modulation, PWM peripheral. So let's take a look at that. And let's see if there's anything more specific in this one quick as well. Doesn't look like it. So this is what we want to read. Chapter 15, pulse width modulation peripheral. This chapter describes the operation of the E300 pulse width modulation peripheral. PWM overview. Figure 15.1 shows an overview of the PWM peripheral. Okay, so we've got another schematic here. So the default configuration described here has 4 independent PWM comparators, but custom configurations with NCMP comparators are available on request. The PWM block can generate multiple types of waveform on GPIO output pins, and can also be used to generate several forms of internal timer interrupt. The comparator results are captured in the PWM CMP, XIP, flops, and then fed to the PLIC as potential interrupt sources. The PWMC XIP outputs are further processed by an output ganging stage before being fed to the GPIOs. The PWM unit can be provided in different comparator precisions up to 16 bits, with the version described here having the full 16 bits. To support clock scaling, the PWM count register is 15 bits wider than the comparator precision. So, what I'm understanding from this so far is PWM is all about pulse width modulation. So we're talking about generating waveforms, right? So think like a sine wave. So then what I'm wondering is, are we getting different colors and intensities by like altering patterns in the pins really fast? Or is that not, like, because we're sending waveforms over the pins is the idea here, right? So we've got a memory map. Okay, so this is a config register, 32 bits, and it has a bunch of stuff in here. Okay. So, I mean, part of what I'm wondering about GPIO is like, can we send different intensities over the pin? Or is it purely like you can send a 1 and a 0? Is it totally binary? Because like we have one pin for each channel for the LED. And so like right now, what we were doing with GPIO, we were just messing with single bits to turn the channel on or off. And I'm wondering, like, when you're sending data over a pin, are you only sending, you know, a stream of single bits over that pin? So like if you're only sending a stream of single bits, then you'd have to get different colors by flickering it flickering the channels on and off really fast, right? Whereas if you can send more than that over a pin, then you could actually like alter the intensity. Or if the LED were to like sample sections of a stream, like so many bits at a time or something. So to support clock scaling, the PWM count register is 15 bits wider than the comparator precision, comparator width. Okay, so the output is only 0 or 3.3 or 5, which would be depending on the IORF jumper. It's digital, so that makes sense. The PWM is just a pulse wave, but you can tell it how long to be on or off. This way the average output is no longer 0 or 5, but anything in between. What I don't understand is how we're sending, like, how is the wave represented? Like, let me open Milton to say what I mean. I'll draw it out what I'm thinking. Okay, let me find some space. Okay, let's put it right here. So I'll go into grid mode here, and I'll try to draw a decent wave. So if I say like so that's pretty terrible, but there's my attempt at a wave. So I mean, if we're talking digital, we can only, like, when I think of a wave, I'm thinking like this axis right here is time, right? And then this axis right here, I think of as being like value or intensity of the wave, right? So if we have another thing here, and we're going to say this axis again is time, and now we're representing what the stream of bits we're sending over the pin is. So we're sending pulses of 3.3 or 5 volts, right, across the pin. And the absence of a pulse is a 0, and a pulse of, you know, when you send the line high, that's a 1. And so it's a digital signal. But now this axis right here represents the value of the pulse that you send. So it's only ever going to be 1 or 0, let's say, right? Since it's a digital signal. So if we can only have 1s and 0s, how do we represent this waveform that we see up here, down here? That's what I don't understand, like how we're making a wave out of this. Thank you for the link, Hossein. I will take a look. Okay. Okay, here we are. So this diagram right here shows what we're doing. So this is voltage. This is B, which I take to mean the approximated waveform, right? So V goes from -1 to 1, and there's 0. So wait a minute. That's 3 different states V is in. Right. I get that the red line is the average. But what about when it's 0? Like, you're saying that the PWM value is only 1 or -1, but as I look in this diagram, I see pulses of like pulses that go to 1. So you see it rises, it hits 1, and then it falls each time you send a 1 pulse. And so you can vary the length of that pulse. But then you can also send a -1. Yeah, I think I mentioned that, and it's just Twitch lag here, where we're saying the width of the pulse. To get the average. Or maybe I'm not understanding. You're saying one more thing to look is the width of the pulse. If the pulse is 50% 1 and 50% 0, the average is 0. Okay, so like from 0 to just a little bit forward where we see the rising edge of the pulse, that's 0 in this red line, which is the average. I don't know if that's what you mean or not. I want to read this because I clearly don't know anything about this. So, an example of PWM in an idealized inductor driven by a voltage source modulated as a series of pulses resulting in a sine-like current in the inductor. The rectangular voltage pulses nonetheless result in a more and more smooth current waveform as the switching frequency increases. Note that the current waveform is the integral of the voltage waveform. So this is a modulation technique used to encode a message into a pulsing signal. So I need to take a look at a pulse in signal processing. Like, I understand what a pulse is, but I feel like I need more of a background here. So, I mean, that's not really that interesting. So, can be used to encode information for transmission. Its main use is to allow the control of the power supply to electrical devices. So the average value of voltage and current fed to the load is controlled by turning the switch between supply and load on and off at a fast rate. The longer the switch is on compared to the off periods, the higher the total power supply to the load. The PWM switching frequency has to be much higher than what would affect the load, which is to say that the resultant waveform perceived by the load must be as smooth as possible. The rate at which the power supply must switch can vary greatly depending on load and application. Okay, voltage. So we've got some physics there that I'm sure I studied at some point. See, what I'm still confused about is, like, we're saying this blue in this diagram represents voltage. So, like, you can send pulses. My confusion is, like, the default is like 0, right? Like, if you're not sending any voltage over the line, you just get this 0, right? And then what we're doing is we're sending pulses of 1 and -1. So when we're talking about zeros and ones in circuitry, in binary, like, as a computer programmer, I always think about it as 0 and 1. But in terms of actual circuitry, there's actually 3 states, if I'm understanding this correctly. And what we call a 0 in programming is actually pulling the line low, and what we call a 1 is pulling the line high. Is that correct? Or am I totally misunderstanding this? You don't know the third state you were talking about. The third state I'm talking about is when the line is when you're not pulling it in either direction. So, like if you're not doing anything on the line, it's just 0, right? Like in this diagram, it would just be a flat line on 0. And then you have two possible states that you can put the line in, which is you can pull the line high, which is 1 in this diagram, or you can pull the line low, which is -1. So if I'm not doing anything, it's neither 1 or -1. We don't have negative voltage, so it's 0 or 3.3/5. But I'm talking about on this diagram where it's labeled from -1.5 to 1.5 on the y-axis. So I'm not necessarily saying -1 volts. It could be like, let's say that low is the 3.3 and high is 5 or something, right? Like in this diagram, you see that the pulse either goes up or it goes down. Like how are we getting that direction? Like in this diagram, I see 3 different states. There's when it's on 0, when it's on 1, and when it's on -1. And that's 3 different states rather than 2. Like, I get what you're saying, that we don't have negative voltage. It's 0 or 3.3 or 5. But then if it's only 0 or like 3.3 or 5 or whatever you set the high one to be, then what's the in between? Do we have the resting state being like halfway between 0 and the high state? So like would in this diagram, if we say -1.5 is 0 and we say 1 up here is like 5 volts, or let's say -1 down here on this diagram, that we're going to call 0 volts, and then we're going to call 1 up here 5 volts. So we can toggle it between 0 down here and pull the line low, or we can toggle it to 5 volts and pull the line high. But then what's this in-between state? Is it like resting at 2.5 volts then? That's what I don't understand. Maybe this diagram is just deceptive. Okay, what are you saying? So for the pin to detect 1 in binary, the pin voltage should be within a threshold, say 3 to 3.3 volts. For binary 0, it should be between 0 and 0.5. And the in-between voltage is not valid. Okay. So maybe I'm misunderstanding what this diagram represents. What V represents in this. Because there are times in this diagram where V would be invalid in binary then. Anytime V is being held on 0, that doesn't make sense in this diagram. So the voltage threshold is dictated by the CMOS process. So I like these ASCII diagrams here because they're showing 2 states. Like this makes sense to me in terms of digital because we have the low and we have the high, and there's not like a resting state in between them. So we're saying this is a PWM signal here. So we have a long 0, and then we send a pulse. We wait, we send a pulse, and the pulses vary in length. So what I want to find is another diagram like this that shows the digital signal and then has like the waveform. I want to see how the waveform like gets represented digitally. Because this diagram, like that's not a digital signal. So I don't understand what it's trying to tell me. So let me see if I can find like a visualization of this. PWM visualization. So we've got a paper here. I don't know if that's what we're looking for. Can I get images? So here we see a digital signal on the bottom. And I take it this is the waveform being represented on the top here. So the key to it is really how long the signals are. So I'm getting a better understanding of this now. It really has to do with the length of the pulses to determine the waveform. I think what I really am trying to understand here is this is like the Claude Shannon sampling theorem, right? The process of PWM conversion is nonlinear and is generally supposed that low-pass filter signal recovery is imperfect for PWM. The PWM sampling theorem shows that the PWM conversion can be perfect. So we're talking about the representation of analog signals as PWM waveforms, which are these approximations, and that they can be one-to-one. That's what the PWM sampling theorem is all about. So Nyquist samples, I'm not familiar with that terminology. So the other key thing that we're talking about is averaging, right? So based on the length of the pulses, the averages are determining the curve. So here we have a pulse wave. So let's ignore this one right here and look at some of these because these look like digital signals. So like this is a digital signal on the bottom here. So I still feel like I'm kind of struggling to fully understand this. I want to get a good intuition for what we're talking about. And I don't feel that I've got that yet. But I think we're out of time for today too. So I might just have to sleep on this and maybe I'll get maybe my brain will get it to all click together when I'm, falling asleep. Sometimes that happens. So Thank you everyone who tuned in tonight, and thank you everyone who watches on the YouTube archive at risky.tv. And you can follow me at HMN_risky to get updates about this series. I will see you in the next episode, and stay risky, everyone.